Hey, Mr. Roark here, and in this video we're going to review concepts from Unit 1. So we're going to go over everything that has to do with kinematics in a constant velocity. We'll review concepts that have to do with graphing, of course, and we'll look at the equations again. I'm not going to spend a lot of time talking about Unit 1 because most of the things that we covered in Unit 1 we went on and applied in Unit 2. If you remember, Unit 1 was all about constant velocity. And so when we went on and studied acceleration and changing velocity, we really took all of the concepts and just moved them over and looked at that. And so most of the stuff we're going to look at on the final is just going to be in terms of that accelerated reference frame. But one thing that I definitely think we need another look at is writing an equation for a line. Because a lot of people still seem to be struggling with this. So we have a graph here, and of course, we need to make a best fit line. So let's take a line here, something like this. I'm going to need to adjust this a little bit. Actually, that looks pretty good. Now notice here, I extended the line so it actually hits the axis over here. I need to know where that spot is. So I don't just want to start at the first dot right here. We want to extend the line all the way because we need to know that spot. So remember, we write the equation based on the format y equals m times x plus b. But one of the things I see a lot of students still doing is, because the first couple of graphs that we did were position versus time graphs, I see a lot of people just going, oh, this has to be x equals something times t. But remember, you have to build the whole equation from the actual graph. The only way we would have x right here is if this was position on this axis, but it's not. In this case, this is a velocity versus position graph. So you really need to learn how to build these equations from the graph that you have and not just memorize what's going on. So let's get rid of that. Okay, so let's go piece by piece. Y comes from the measurement on the y-axis. Now you have to be careful here. We're looking at what's actually being measured, not the units. The units can only go along with numbers. So meters per second will go along with numbers. What we're actually measuring on the y-axis is the velocity. And of course, the symbol for velocity is v. So we have v equals m is the slope. So we need to find the slope of our graph. So I'm going to pick 2 points on the line. Let's see. That would be some good points here. Let's see. Let's take this point right here. And, well, let's look at, I think, here at 12. We can pretty much figure out what that would be as well. We need to find the slope. So we're going to find the change in the y-axis, and we're going to divide that by the change in the x-axis. So the change in the y-axis, it looks like I start out actually a little bit below 25 meters per second. And it goes up to 50 meters per second. So I think this is going to start at 24. So from 24 to 50 meters per second, that would be a change of 26 meters per second. Horizontal axis, I drew this first dot here at 4 meters. I drew the second dot at 12 meters. So in the horizontal axis, we have a change of 8 meters. So to find my slope here, I'm going to take 26 meters per second and divide it by 8 meters. And it's important to put the units in there when you're doing the slope, because the slope, when you put it into the equation, it has to have the correct units. And it's easiest to see what those units are if you actually do the math with the units as well. A lot of times people leave these out, and then they're just throwing in whatever units they think they should be. And for whatever reason, you're not figuring those out right, and you're just guessing. So if we actually look at the change here in meters per second, because that's what's being measured on the vertical axis, and we look at the change here in meters, because that's what's being measured on the horizontal axis, when we divide this, and we take 26 divided by 8, which would be 3.25, the units have to come along with. We get meters per second divided by meters. That is the actual slope, and that goes into our equation. So we can put that in for m over here. 3.25 meters per second divided by meters. Okay, now the next part, x in the equation, comes from what is being measured on the horizontal, or the x-axis. Now in this case, again, it's not meters. We don't say we're measuring the meters there. Meters is the unit that we use to describe the measurement. We're actually measuring position. And the symbol for position is x. So in this case, we're going to put in x. And then the last part of our equation, plus b. B stands for the vertical intercept. Basically, that's just where this line that I drew hits on the axis. And that's why I needed to draw that line all the way over there. So you see it hits right here. I would call that about 12 meters per second. So we need to put that into our equation. Plus 12 meters per second. And now we have an equation that completely describes our graph. Our equation says the velocity of our object is going to be equal to 3.25 meters per second divided by meters multiplied by the position that the object is at plus a starting velocity of 12 meters per second. Remember, this tells us how much, or what the initial value was, in this case what the initial velocity was, and our slope here tells us how much the velocity changes for every meter that you go along. So as your position changes, how much your velocity in this case increases, and we can see it goes up. Now if you know how to actually build an equation, then it wouldn't matter if I gave you a velocity versus time graph, or a position versus time graph, or a temperature versus pressure graph. It doesn't matter what kind of graph you get if you know how to build the equation. And because on the test you could get a position versus time graph or a velocity versus time graph and be asked to write the equations for those lines, you got to be able to build it. You can't just memorize one type and just hope that it's going to be X in the same place every time. You really need to learn how to put the thing together. Look at the equation sheet for Unit 1. In Unit 1, we basically have two equations that we're going to focus on. So let's take a look at this first one here. Delta x is equal to xf minus xi. This is really just a mathematical definition of displacement. Okay? Displacement, delta x, is really just change in position. Remember, delta or the triangle means change. So this tells us the displacement, also known as change in position. And just like any type of change equation, when we find the change in position, we take the final position and subtract the initial position. And it is important to do it in that order so that you get your direction signs right. A positive displacement tells us that the object is moving towards the positive end of the number line. A negative displacement would mean it's moving back towards the negative end of the number line. And that's important when you're looking at change in position. Now our other equation here, we have V equals delta x divided by delta t. This right here is the mathematical definition of average velocity. It says the average velocity for an object is equal to the change in position divided by the time. Now this is just an average. Okay, really it should have a line over it. The line keeps getting left off when I print this thing out. So the change in position divided by time really just gives you an average, and it's only useful to find the actual velocity if the object is going a constant velocity. If the thing is speeding up or slowing down, you can still get an average by using this equation. You can still find the average velocity by taking the change in position divided by the time. But it's only going to tell you the average. It will not tell you how fast it's going at a certain point in time. And I see a lot of students making a big mistake here in trying to use this to find the velocity of an object given, you know, in a kinetic energy problem where you have a force put on it over a distance and it's speeding up or slowing down. So this is really not that useful unless the object is going at constant velocity. So if you note the thing is not speeding up or slowing down, then you can find the velocity simply by taking that change in position and dividing it by the time.